Alright, you're here to watch the lesson 6.4 video. But before we do that, I'd like to show you this little applet. Remember in the 6.2 supplement where we talked about estimating the area underneath the curve using rectangles? Well, here's a visual picture of what we did. See? A whole bunch of rectangles. This one uses the left endpoint. I could change it to the midpoint, I think. And then if I wanted to use the right point, that's what we have. And notice that as I increase the number of rectangles, the approximation gets more and more accurate. Almost so that it actually equals to the area under the curve. And what did I say it was if I equaled it to the area underneath the curve? Pretty much the definite integral. Yeah. Now, let me just show you what happens if we draw trapezoids as well. So here's my first trapezoid. Here's one with 4 trapezoids. More. And notice that once again, I'm getting a better approximation. And once again, as n goes really large, the number of rectangles getting big, it equals to the definite integral. Now I show you this because today's topic is about area between curves. So really I'm asking you to find the area between two graphs. Notice in this example I've got my line y equals x plus 4, and I have my parabola y equals x squared minus 2x. I want you to find the area between the curve from here at -1 all the way to 4. Okay. Now notice right now I have 3 what I call partitions or rectangles. I can move it back to 2 perhaps. Oops. Where'd it go? 2. 2 rectangles. 1 no rectangles. So notice what happens once again. As I increase the number of rectangles, you'll see that I get closer and closer to the actual area between the two curves. Beautiful. Beautiful. So our goal today is to really figure out how to calculate this. Not as an approximation, but actually as an exact answer. Now I want you to keep this in mind, okay? Focus in on one of these rectangles, okay? As we then go to our notes. Alright, now before we even begin our notes, I know you don't have this, but our goal once again is to do what? Is to find the area between two graphs. Okay? Now notice there are intersection points, so let me just call this point here A, and let me call this point here B. So how in the world can we find the area between these two curves? May I suggest using something we've learned before? Just visualize, you don't need to write this down. Let us take a look at the line. Oops. I should have drawn that in blue. From A to B. We know how to do this. To find the area in here. Right? That would be the integral from A to B of that function. Let me call that function f of x. Right? We also know how to find the area of this particular function, also from A to B. What would this be called using our calculus notation? Well, if I call this function g of x, that's what you have. And so ultimately, what happens if I take this one in blue and subtract the part in red? Hopefully you will see that you just get what we started with earlier. And that just happens to be the area between the curves. So ultimately, it's really just the integral of a to b of the f of x function, or the higher function, the higher graph, minus the integral from a to b of g of x, which represents the lower function. And if you think about that little rectangle here, let me just draw one for example. Notice that to find the area of that rectangle, it's your delta x, which is your width, times the height of that rectangle. Now the height of that rectangle is really given by the following. The distance from there to the x-axis is called f of x. The distance from the bottom of the rectangle to the x-axis is your g of x. So really that height here is equal to the difference between f of x and g of x, which really is the higher function minus the lower function, which is what you have here. So friends, if you understand this concept, then you've already mastered how to find the area between curves. Let's take a look at your notes now. Alright, here we go. So, like what I just said earlier, the area of a region between two curves is really the integral from a to b, and what's in a to b are your intersection points of the function f of x, which is the higher one, minus g of x, which is the lower one. And you've got to make sure that both f and g are continuous functions, and like I said, f is always bigger or equal to g over that interval ab. Okay? Sometimes people will use this. They'll say the top curve minus the bottom curve. Alright? Now, don't worry about that next statement yet. We'll go to that in a moment. But let's just focus on example number 1 now. So I said find the area of the region bounded by y equals x squared plus 2. That's this one here. So that's y equals x squared plus 2. Y equals x. That's this one down here. X equals to 0. That's this line here. And x equals to 1. Okay? So in this case, there's no intersection point, but visualize once again us creating these vertical rectangles, and summing them all up. Okay. So as I create these vertical rectangles, notice what I'm doing is I'm finding the area, and I'm integrating starting at x equal to 0 and ending at x equal to 1. And because I am integrating with respect to x as I draw these vertical triangles, or not triangles, rectangles, and I keep moving from left to right, you'll know that this is in terms of x, so I'm going to put dx there. And the key thing for us to understand is what is the top curve and what is the bottom curve. Can you see that the top curve is x squared plus 2? And can you see the bottom curve is x? So there you have it. You've set up your equation to find the area between these two curves. Now, ultimately, can we do some anti-differentiation? So the antiderivative of x squared is just x cubed over 3. The antiderivative of positive 2 is 2x. And the antiderivative of negative x is 1/2 x squared. And we want to evaluate this from x equal to 1 to 0 by plugging in the values. Let's see what we get. 1/3 plus 2 minus 1/2. Then we'll take away 0 plus 0 minus 0. So 1/3 plus 2 is 2 1/3. minus 1/2. I believe that's just 11 over 6, or 1 5/6. Okay, there you go. Okay. Now, in our first example, we didn't have intersection points. However, sometimes you will have to find out where the two curves intersect to determine the boundaries for your regions. Now, these intersection points will provide you with the limits, the values of a to b. Okay? So sometimes your intersection points might not be nice numbers, and if they are decimals, when you're using a calculator, make sure you also show the equation setup. So show me that you've made the two equations equal each other, and then find the answer using the calculator. Now, let's look at this example, example number 2. Some twists here. Notice this one has a function of y, meaning instead of having y equals 2, it's now x equals 2. So how do we graph out this particular function? Well, this would be a parabola because it's squared, but this would be a sideways parabola. And I believe that the vertex would be here at -3. And if you think about what's going on, you'll have a sideways parabola like this. So there's the equation x equals to y squared minus 3. The equation y equals x squared plus 1, or sorry, x plus 1, that's just a nice line. And there you have it. Y equals to x plus 1. Okay? Alright. Now, if you are holding on to your pencil, put it down. As I do the next part, just watch and listen. If I use the same concept from example number 1, then I am creating rectangles like this. And I'm summing them along the x, which is sort of fine. Why do I say sort of fine? Remember, the idea here is you're looking for the height as the difference between the top function minus the bottom function. Well, the top function always seems to be this function in red. That's great. But look at the bottom function. The bottom function seems to be this part in red, but then it changes to this part in blue. So even though this is possible, you would have to set up actually two separate integrals. One for this particular part, and then another one for this particular part. And then add them up. Which is fine, but that sounds like a lot of work. So that's why in this particular example, I want to show you how we can find the area of this graph here by also using what they call a function of y. And what do I mean by a function of y? That's what it says here, by the way. Well, this is what I mean. Instead of making those vertical rectangles, let us now draw horizontal ones. Whoa. And notice that as I draw horizontal ones, I'm no longer looking at vertical pieces for my height. I am looking at horizontal pieces. And to figure out the height, I guess you can say, of the rectangle, that horizontal height, I'll say, it is now going to be found by taking the difference between the two graphs. In this case, not the top minus the bottom, but the right curve minus the left curve. And now I'd like you to focus back on the top here. This is why it says for functions of y, the area is integral from a to b. It's now the right-hand curve minus the left-hand curve. Okay? But these, of course, are functions of y. So even these values a and b here are values that are y. Okay? Y values. So ultimately here, what you should do is you should find the intersection points with respect to the variable y. Which means, and you can start picking your pencil again now and start doing this, you need to change this into an equation that's solved for x. So in this case, x would be equal to y minus 1. And so now I would ask you to find the intersection points first by making the two equations equal to each other. So y minus 1 equals to y squared minus 3. Move everything to one side. Factor. And solve. Y equals to 2. Y equals to negative 1. So the intersection point here is 2, and this intersection point here down here is negative 1. So now if I set up my area integral, it'd be from negative 1 to 2. And notice now everything is in terms of dy. It would not be the top function minus the bottom, but the right function minus the left. The right function in this case is the blue one. Sorry, not the blue one, the green one, which is y minus 1. And then the left function would be the blue one, y squared minus 3. And now you're ready to find the antiderivative and evaluate. Maybe what I'll do before even doing that is I'll combine like terms, and I'll put this as y plus 2 minus y squared dy. Yeah. And now I'll anti-differentiate. And our goal here is now to plug in the values of 2 and negative 1. I'll continue to do that. 2 squared 4 divided by 2 is 2. So 2 plus 4 minus 8/3. Take away from that 1/2 minus 2 plus 1/3. And if you do all this work, which I know you will, you'll get the answer 9/2. Okay. So I've shown you two examples now. The third one, I just want you to set up the integral. So I don't want you to actually calculate what it is, but I do want you to set it up. And this one says you may use a calculator, meaning you probably will need it. So you bring it up. Hopefully you can see what the functions are. One is x cubed minus x. That most likely is this one, the cubic function. And then you've got this g of x, which is a parabola. Hopefully you can see that it would be this one here. And notice the first thing you should do is actually find the intersection points. Okay? And if you were to do that, you're making x cubed minus x squared equals negative x squared plus 4.1x. Which really means you're solving, what, x cubed minus 4.1 x is equal to 0. Factoring in x, I get this, x squared minus 4.1 equals 0. And so you have here x equal to 0. And x squared equals to 4.1, so x equals to plus or minus the square root of 4.1. What in the world is that? About 2.025. Okay, so equals 2.025. Plus minus because, yes, there are two values there. Okay. So now, how would you go about finding the area? Well, notice you have actually the area between the two curves. There are actually two different regions. So what you should be thinking is, let's set up the integral separately for the two regions. And then ultimately, to find the area between those curves, you'd add those two together. So let's take a look at the yellow region first. what are my limits for this area integral? I'm starting here, which is negative 2.025, and I'm ending right here, so the x value is 0. Now once again, what's my top function? What's my bottom one? In this particular region, my top one is x cubed minus x squared, and my bottom one is the parabola, so negative x squared plus 4.1x, and of course don't forget this is all with dx. And now the region in blue, so I'm going to add to that another integral, and the integral in this case would be from 0 to positive 2.025. And the upper function, or the higher function in this case, is the parabola, so we'll start off with that. And then we'll take away the cubic function, x cubed minus x squared. And the whole thing, don't forget, has a dx. And this would be the setup. And thankfully, you don't have to get the answer, but I hope you understand the concept. Okay? All right. So that's it for area between the curve. There's one more idea I want to talk to you about today, so can you turn the page in your notes? And I want to talk about this idea of average value. Now, the average value is really the average height of a function over a certain interval. So this is the idea. I've got a function. Whee! Okay. The goal is, if I were to even this out or balance this out, what would the average height be of this function? Here? 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 Where would it be? Okay? So that's our goal. Now, if you want to see a visual of this, let me just pull up this here. I'm going to ask us to create a graph. And in this case, let's just create a graph by moving things. Hey, hello, woo, cool graph. Yeah. Okay. Yeah. Notice that as I move the graph, you got this horizontal line. So really what I'm saying right now is, as I change my graph by making it higher or lower, noticing that line goes higher or lower. And ultimately that line is really saying, if I were to take this area in green and average it out over the interval, what would that rectangle look like? And that's what this shaded gray rectangle is. Okay, so again, once again, I'm trying to change the height of my function. I got some crazy function. If I average it out, what would it be? Okay, so imagine just taking it and squishing the area together so that you create this rectangle. And that's the idea. So notice we did part 1 already. Draw a horizontal segment from A to B in the figure at the right, which could represent the average height. So I'm going to predict maybe something like this. Maybe this could be the average height. Now if I ask you to find the area of the rectangle formed, I'm asking you to find this. And to do that, the width would be the difference between B minus A. And we'll multiply by some sort of height. Okay? Now the key thing here is that this area here, this area of the rectangle area is the same as the area under the curve that I'm going to now shade in green. It's supposed to be the same. And that area underneath the curve is given by the definite integral. And the area of the rectangle is given by this b minus a times height, which we just got from above. So if I'm asking you to figure out what this average height is, that's the red line I just drew here, I'm really asking you to solve for the height. So if I ask you to solve for the height, notice that the height will just be equal to the area under the curve, this definite integral, divided by b minus a. And ladies and gentlemen, and everybody else, we have the following formula. The average value of a function. Well, the average value of any function f of x over the interval from a to b can be written as f of c. So this is really the y value, right? Or sometimes they'll use this thing called f-avg, or f average. And it's really just the area of the region. So the integral from a to b, f of x dx, divided by the width of the region, which is b minus a. Or more commonly seen in textbooks, it's 1 divided by b minus a times the integral from a to b of f of x dx. Just make sure to note that the function must be continuous over the entire closed interval. So knowing that, let's just apply this to examples 4 and 5. I've got a function here. Can you find the average value of this over the interval 0, 2 without using the calculator? Meaning f average will be equal to the integral from 0 to 2 of the function, x cubed minus x dx, divided by b minus a, which would be just 2 minus 0. That 2 minus 0 just happens to be a nice fraction of 1/2. I can start finding the antiderivative. And now please evaluate it from 0 to 2. 2 squared, or sorry, 2 to the power 4 is 16, divided by 4 is 4. 2 squared is 4, divided by 2 is 2. And then 0 minus 0. And so the answer here is equal to 1. So ultimately what I'm saying to you now is that the average value of the shaded area from 0 to 2, so once again that's this area here, that I'm shading in, and some underneath that I'm also shading in, that average value is really here, 1. So there's your average value, or the average height. Okay. Now let me introduce to you this idea of f of c. So this is now continuing with this example. Use your calculator to find the value of c in the interval from 0 to 2, where f of c equals to the average value. So now what I'm saying is, look at that line in blue. Can you figure out the x value, and we'll call that c, that gives me that particular y value? So ultimately, I want you to make the function x cubed minus x equal to the y value we've actually calculated as the average height, which is 1. And in order to solve this, you'll have to probably use your calculator, and I would say graph it out. In this particular case, I'm graphing out x cubed minus x minus 1. Let's zoom standard, and I'm looking for where it equals to 0. Use your trusty calculator features to do this. There's my left, there's my right, there's my guess, and voila. The 0 is 1.325. So x equals to 1.325 from the calculator. Okay, those are the two concepts for 6.4. I hope you understand this pretty well, and now it's time to test it out by working on some problems.